always we cannot 90% we can believe, but 10% if something happens and you are going to miss everything. So please be attentive, please take a note. Okay, so write down everything which we are going to see now. So first, let me tell you something about our heart. Okay, so more or less everybody would have gone through ECG. So ECG is like doctors will put some sensors around our body. They'll get some electrical signals. From that, they'll get some graph. From that, what they'll do is they will say whether our heart is functioning good or not. Okay. So this is the general representation of a simple mathematical model, because a heart while beating will generate electrical signals. We are just generating a graph from that. So from that graph is nothing but accumulation of data. So from that graph, we can able to create an equation. From that equation, we can exactly model our heart, behavior of our heart. Okay. So what is the use of this? Use of that? You can exactly tell each and every motion of your heart just by having that particular equation. Okay, you can just predict what will be the heart's volume while your curve is in this position. Likewise, you can exactly tell all the characteristics of the heart just by having some numerical data. So this is the importance of mathematical modeling. Even now, amidst corona, a lot of universities, John Hopkins, if you take Indian Medical Research Council, everybody is telling, like they told, like in May you will have a peak infection, in September you will have a peak infection, in July you will have a, likewise they predicted so many things. Everything is possible only via mathematical modeling. You can do all the things in Simulink. Okay, just you should have a data. With the data, by doing some regression analysis, you can create a math equation. With that math equation, you can create a mathematical model to predict whatever variables you want to. Okay, so this is the wonder of mathematical modeling. So when I was doing my 8th standard or 9th standard, at that time I just got introduced to differential calculus. Okay, so that was very new to me. One day I was just I had a doubt in differential calculus. It is like, will that calculus able to exactly predict the changes in volume of something. Okay, at that time I took some cuboid. I just wanted to predict how water flows in it. I want to predict the changes with respect to time, because I don't believe that differential calculus would be able to predict everything exactly. So after performing so much computation, I finally convinced myself that by doing differential calculus, I just able to exactly predict that. So at that time I wondered how maths works. But now I know you can predict any real system exactly by creating a mathematical model. So that's very important. Okay, so today we are going to take two things. One is battery model, another one is a mass spring damper. Both things is common for all departments. Okay, because the same procedure you are going to use. If you are from AEC-EEE, you are going to create a mathematical model of digital signal processing or whatever it is. Everything is same, because partial differential equation, differential calculus, integral calculus are same for all departments. Only thing is the application changes. Okay, so everybody, please put your mind, learn something from this session so that you will be able to create your own mathematical model. Okay, so that's what I want to tell you before I start my session. So now let me start my session. Okay, so our first project for today is to create a battery model. So when I say battery model, so most of the times, in the recent days, EV is getting so much familiarized. Now they have something called million-mile batteries. Likewise, there is so many advancements, and each time, you cannot create a real battery, test it for a different current, test it for different voltage, test it for different temperature. That's nearly impossible. Okay, because stuffs like batteries, if you go beyond some temperature, it will burst. Thing will go out of control. A lot of problems are there, cost is there, time is there, so a lot of stuffs are there. So in order to save all these, the best possible way is to exactly model the behavior of that particular battery. If you can model your heart, battery is nothing, okay, because heart is a very complicated system, lot of variables are involved in that. If you can model that, battery is simple. Just we have around 3 to 4 parameters, um, voltage, current, discharge resistance, as well recharge resistance. Likewise, we have few variables, so we can easily exactly model the mathematical model of battery. Okay, fine. So in the screen you can see we have three images: full battery, half battery, battery at critical level. Okay, so this is the exact battery, this is the battery model, which means our math model. Okay, so what we are going to do is we are going to give input in the form of current. For example, you take your mobile phone. What we are going to do is you are going to put charging means you are going to supply current I. Okay, so with respect to that, you are going to get increase in voltage in that particular battery. Okay, so if this thing is satisfied by this particular model, then our model is 100% correct. But if it doesn't satisfy, you will get something called error. Okay, our ultimate aim is to reduce error, so that's why we are going to use PID controller. uh, you know in creating a today I'm going to tell you how to create a PID controller manually, but tomorrow sessions you will see how to use a shortcut of PID controller. You should know both, because as a UG students, if you use automatic PID controllers, that's fine, but at a higher level we should definitely. Guys, I hope everyone is getting my audio. If there is any problem, please tell me. Is there an issue in my audio? My audio is not. Okay, once again I'll check. Fine. Is this is now clear? Is my voice clear? Fine, fine. Okay. Some of the students may have a network issue, so please check. Fine. So yeah, that's what I'm telling. So we have a exact battery. So we are going to create a battery model. So you are going to give current. You are going to measure the voltage variation in your battery. Okay. So in order to do this practical thing, you are going to create a mathematical model of your battery. Okay. So this is the content for our first project. But before that, I want to tell you something, some important things. So please listen carefully. So throughout the session, you are going to hear something called open circuit voltage. So open circuit voltage is nothing but, yes, fine. So the open circuit voltage, throughout the session, you are going to hear frequently the term called open circuit voltage. Okay. So the open circuit voltage is nothing but, if you take a multimeter and measure the voltage of the battery, which is not connected to any load, then that is known as open circuit voltage. Very, very simple. Okay. But why we are giving so much importance for open circuit voltage? Because your state of charge, SOC, is directly proportional to open circuit voltage. That I'll tell you shortly. Then what is closed circuit voltage? It's nothing but, if you have a particular load, then the voltage if measured is known as closed circuit voltage. Okay, so this two terms is important. Next one is, as I told earlier, open circuit voltage is the direct function of state of charge. So that's the reason if you go to any shop and show your battery. Okay, so what they'll first do is they'll take a multimeter, they'll measure the voltage. So based on the voltage, they'll tell you what is the state of charge, what is the percentage of charge available, whether it can be recharged or the battery is dead. Okay, so everything can be measured with the help of OCV. Okay, so today we are going to give so much importance for OCV. Next one is, yeah, this is what I am speaking about. So the relation between open circuit voltage and state of charge. Okay, so as I told, we have our heart. Okay, pardon me. So just assume this is heart. What happens is, if you take ECG measurement, what happens is you will get something like this graph, something like this. So this particular graph can be converted to a mathematical equation. If you are able to convert this particular data to math equation at each point, what you can do is you can exactly define your heart position. What is the volume of blood in it, how it is pumping, everything you can exactly predict. Okay, so if you can predict a very complex system of nature, then battery is nothing. On one hand you will plot a voltage, on other hand you will plot a state of charge. So if you make a linear relationship, from that point you can measure the state of charge. Alternatively, if you know the state of charge, you can know the battery voltage. Okay, so this is what we are going to do. And if you see here, we have two graphs. Battery will behave, distinctly while charging as well discharging. That is because if the battery is dead, you will have a different resistance. If your battery is full, you have a different resistance. So this major changes is responsible for heat generation while charging as well discharging. Okay, so in order to predict the exact behavior of the battery, what I am going to do is I am going to take the average of this two graphs. So from this line you may not understand something, but I'll make it thin. See, from this particular graph, I'll create the average between charging graph and discharging graph, so that I can exactly, because I don't want my battery only to behave how it is getting charged or discharged. I want the touch of both. Okay, so I'm going to take the average. So if you take the average, so this is how the graph will look like. Okay, so this is the average behavior by reducing the error, how your battery will function when it's getting charged as well discharged. Okay guys, so I hope you are following me. I hope you are getting, I hope till now you understand everything. So if there is any doubt, please ask me, so that I will show you the math equation to define this particular graph, and I will show you how to create that, how to simulate it, everything I will show you. So if you understood so far, please put S so that we can proceed. Any doubts, please put it in the screen. So I'll clear the doubt, we move forward. Others? Okay, fine. Okay, we proceed. So again, a small... Abhinash, can I know what is the use of it? Without knowing the application, definitely you cannot say what is the use of it. So please be patient, so that after at the end you will not ask this question. Fine. So I hope everybody understood. So we can move forward. So again, I am telling you, battery will behave distinctly while it's getting charged and discharged. That is because of charging resistance as well discharging resistance. In order to have the essence of both, I am just getting, combining all, I'm just getting this particular graphical representation. Okay, so in order to represent this particular battery, I have a math model. Okay, so this is just, as I already told, what happens is, if you know the open circuit voltage, by using multimeter, if you measure the OCV, you can know the state of charge. This is how most of our SOC indicators work. For example, in mobile phone, you can see what is the charge at any time. Okay, that's only possible by measuring the OCV of your battery. Okay, fine. After measuring the SOC, you can just display it by using some LED. That's very simple. Measuring that is very difficult. Fine. So now I'm going, yeah. So this is the math equation that represents the particular battery. Okay. So this equation may change for battery to battery, for case to case, but the procedure is same for all system, whether it is mechanical, electrical, EC, triple E, whatever it is, the procedure is same. So please listen carefully. Previous day on Monday, I solved one of the mathematical equation using MATLAB. Okay, so most of you guys had some doubt. So after solving this, definitely I hope you will be clear on those doubts. Okay, let me start now. So now what I'm going to do is, first I'm going to calculate this SOC. I'm going to put this SOC in the terminal voltage formula. From that, I'm going to measure the voltage. So this is what I'm going to do. I'm going to give input current. I'm going to measure the output voltage as we exactly do on a practical systems. So let me start. Fine. So as I already told, whenever you are going to create a Simulink model, it is better to create your script file so that it will be so much beneficial. So I'm just giving the name. Just save it. Already I have those files. I'm just recreating it. Fine. So next what we are supposed to do is, I have already saved it. Go for home, go for Simulink library. So guys, so if you have any doubts, please stop me then and there and clear those doubts so that we can proceed with better clarity. Okay, fine. So now what we are going to build. So if you see it, I am going to create this particular stuff first. Okay, so as I already told, I am going to give current. So I'll minimize it. So as I already told, first what I'm going to do is, I'm going to integrate my current. Okay. So once I integrate my current, I'll get this. Okay. First I'll have small I. So first I'll have my I, which is a current in ampere. After integrating that, I'll get the integration of the particular current. After that, what I'm supposed to do is, I'm going to multiply that value with my gain. So gain value is 1 by Cn. Okay. So after doing this, you will have your Simulink model to give you SOC. Then what I'll do is, I'll substitute that particular SOC over here. I will use something called lookup table. It's like seeing graph. Definitely you would be aware of that. You will have one data. With that data, you will measure the proportional data. Okay. Likewise, we are going to use lookup table and Simulink. With that, you are going to measure OCV as well, R discharge value. From that, you are going to measure your terminal voltage or output voltage. Okay. So this is what we are going to do. So please listen carefully. I'll give you 1 minute time. Please note down this particular equation so that you can understand better while moving on with our Simulink model. Okay. So recently, when I was, few months back, when I was seeing some Naukri and all, I came across one thing very frequently. The main requirement is, whether you are from mechanical or whatever background, you should be aware of creating 1D models. Okay. It's nothing. Okay, 1D model is just creating a model which represents your physical system by using some math equation. Okay, so while moving on to 2D 3D, we have so many complex system numerical methods come into play, but 1D is just analytical approach. Okay, so that's what we are seeing here. We are creating a 1D model to represent our particular battery. Okay, so these approaches have a lot of jobs in the market, so that's why, please make a note of these equations. So while moving on to Simulink, you can tell me what I have to do. I hope you took a note. So let us move. Okay. So I'm just going for Simulink library. Just in here, I'll have a new model. Just click a new model. First, I will save it. Guys, one best practices is give a short name. Okay. Because if you give a big name, you are supposed to make a mistake. So I'll involve this particular Simulink model in my MATLAB script. Okay, you may not understand this, but put it in your mind so that while moving on to that you'll understand. Okay, so what I am going to do is I'm going to give a small name. So already I have bat. So bat mode. Okay, so I'm just giving a small representation. Bat mode. Fine. Now, what I have to do first? So now what I have to do first? Go for math equation. So first, what we are supposed to do is you have to create a block for integration. Okay, that's nothing but an integrator block. So how to do that? So go for this, go for this, go for commonly used block. You will see the integrator over here. Just pick it and place it over here. Okay, so this is nothing but, if you go here, you have your integration of current. Okay, so you have your integration of current. So what I am doing is, go here. So what I'm doing is I'm just bringing in integrator block. So if you see, I'll make this as current I. Okay, so when you integrate your I, what you will get is the term which is mentioned here, guys. So please listen. I'm not doing anything. I just want to integrate my I. In order to integrate that, I'm just bringing my integrator block. So when you see I have my integrator block, the input is I. So that what I'll get output, integration of I, int of my I. Okay. So now I have integrated my current. So you may ask me, where is the current? Where is the output? You may ask me so many doubts. I'll answer it one by one. Okay. Now I have the integration of my current. Next one is the integration of my current is with respect to 0 to t. Okay. So when you take Simulink, we have two things. Okay. One is S domain, another one is time domain. Okay. So now we are going to perform everything in time domain. The model will get variated with respect to time. Okay. So you may not understand this at this point of time, but while moving on to mass spring damper, you will know, what is S domain as well time domain. Fine. Next one is, now my thing is done. I'm going to use time domain. So 0 to t will be taken care of. I have created the integration of my current. Okay. Next, what I'm supposed to do is, I am supposed to multiply the value of gain with this particular current. Okay. So as we already saw, how to bring in gain. Yes, in default, it will be in time domain. We can change that to Laplace domain. I'll tell you. So why I'm telling that is, when you see here, by default, the system will get simulated for 10 seconds. Okay. Fine. So next, what I'm going to do is, I'm going to bring in the gain. So I'm just building step by step. I'm just bringing in my gain. So guys, now I'm not going to use anything in direct. Okay. that day, on Monday, what I did is I gave every value here, I simulated it, I shown you. And I also mentioned in future we will not do that, because if you give one here, this system is for particular case. We don't, as engineers, we don't prefer that. We want to model a very wide range. That's where our profit comes from. So in order to do that, I'm going to put a variable over here. When you go here, the variable is 1 by Cn. Okay, so 1 by Cn. So double click it. 1 divided by Cn. Okay, just put it here, give OK. Fine. So when you just make it bigger, the value will get displayed over here. 1 by Cn. Fine. Now what happens is, I have successfully made this. Okay, fine. Next, what we are supposed to do. Okay, so guys, please listen very, very carefully. I am just saving this. Now I am going for my MATLAB script. Okay, so why MATLAB script? So only from MATLAB script I am going to bring in some data. Okay, so what data? The data to represent current, battery behavior, SOC, everything. Okay, so how to bring in that? So guys, as I already told, first block in, first thing when it comes to MATLAB scripting is these things. Clear all? Close all. Okay, next thing is input block. Input block. So what we are going to input over here? So I'm going to input my Excel sheet. So what Excel sheet? Okay, the Excel sheet which I'm going to use now will represent that particular battery. For example, that's what I mentioned previously. In order to mathematically model your heart, what you need is some data. Okay, some data which is measured by that ECG device. Okay, it's nothing but the sensors will be placed in your heart, in your body. It will be something like that. It will be connected to the ECG. ECG will show you something like this. Okay, so in order to model your heart, what you need is this data. Okay, likewise, in order to model a battery, what you need is some experimental data. Okay, this data we will send you in a Google Classroom. Here I'm going to read it right away. Okay, I'll have that in terms of B_P. Okay, I'll open it and show you. That's nothing but some numerical value. See, this is okay. State of charge, open circuit voltage, charge resistance, discharge resistance. These things are measured from a battery to create a math model. Okay, having this particular data, you can analyze your battery for various case. By just modifying some of the data over here, you can create a new mathematical model to represent your new battery. Likewise, you can do so many things. Okay, so how to bring in that Excel sheet into your thing? So go for MATLAB. Data equal to, the command is XLS read. Okay, so XLS read. Next, create open bracket, put apostrophe. Then I'm going to put in the name of that particular file. If you put a wrong name, you will not be able to open it. So just simple. Okay, data equal to XLS read, the particular name of the file. Abhinash, some of the details will be available in the net. Some of the things may not be available, but this particular model we will give you. These values are not calculated but taken as a, for example, while doing calculations or measurement in your lab, in order to measure the performance of IC engine, or in order to measure the performance of a heat exchanger, what you will do is you will take particular data at particular time. The same. Okay, just by using those data, you can create a mathematical model. For example, nowadays most very popular thing is data science. Data science, what it does is, for example, there is a particular website which sell garments. Okay, what they'll do is they'll create a data in which product, what are the customers are interested in, okay, at what age group they are interested in what product. Likewise, they'll have a numerical data. So these data are taken practically. After that, you will create a math model so that you will predict the, so once you create a math model to represent the behavior of the buyer, then what happens is you can exactly tell the age group of 15, definitely they will go for something like cricket bat, something like that, okay. So yeah, that's very important. That should be in the same folder in which you save your script file. If it is in the other folder, it will not able to read. It will show you some error. Okay. So once you create a mathematical model of the buyer, then it's very simple to predict. If they are in the age group of 18 to 21, then definitely they are going behind some fitness equipment, something like that. If they are women, definitely they are going for some fashion article, something like that. So they can exactly predict, okay. So that's what we are doing technically. So we are going to predict the exact behavior of the battery. So after putting this, what I'm going to do is I'm just going to run it so that the data will be read. Give run. Give some time. Fine. So as you see, there is a data. I'm double clicking it. You'll get a data with 4 columns, 101 rows. Okay. So yes, that day someone asked me why Excel sheet. Doing this much stuff is not possible in any other softwares. Okay. So only by using Excel sheet you can process a huge number of data. Okay. So I successfully imported it. And also you may ask me like why there is we should create a section and all. But now, as you know, in order to import this data, it took me around at least 10 seconds to 20 seconds. Okay. So if I run everything from first, what happens is every time the data will get read. Okay. In order to avoid that, I'll create my new section. Okay. So what happens is I have separated this. So I'm not going to touch this particular section because each time if I run, if there is no sectioning, what happens is MATLAB will read the data from that particular Excel sheet again and again. Again, this is going to be a mess. To avoid that, I created a separate thing. Okay. So now I'm going to segregate the data because the Excel sheet has bulk of data. We don't know what to do with what. So what I'm going to do is I'm going to separate the data. So how I'm going to separate the data? Guys, please listen. Yeah. In order to use Excel sheet, XLSread is a default command. See, first column is state of charge, second column OCV, next is charge resistance, another one is discharge resistance. Likewise, I am going to read data separately. So how to read this data separately? So go down. First, I'm going to read SOC. The thing is, I'm going to read it from data because that's what I named data. Open bracket. I'm going to put a colon. Colon means, I'll tell you that. Next is 1. So what is the significance of this? It's nothing but, if you put a colon, it means the complete column. Okay, rows and column. I'm going to read all data from first column. Okay, so SOC is that first column. I'm going to read all the data from my first column. So if I run it, yes. So see, what I did is I did SOC. I'm going to read my particular data. So this is where it comes from. From this particular data, I'm going to read first column, all rows. If you put colon, it means all rows. Okay. So if you see now, you get SOC separate over here. I'm just opening it. See, complete data to represent your SOC. Okay. So I'm just closing it. So next I'm going to read OCV, open circuit voltage. So OCV equal to same data open bracket all rows of my second column. Okay. Likewise, next I want to write a command to read R charge and R discharge. Can someone tell me that? How I should write it? Can anyone? What is the command I should write in order to read R charge and R discharge data? Yeah, good, same. Yeah, same. So what I'm going to do is, I'm going to name it R charge, which is equal to data, fine, everybody is listening, good, colon 3. Okay, likewise R discharge, which is equal to data colon 4. Okay, so if you run, what happens? It should create me 4 separate things. Yeah, so when you see at the bottom, you have for OCV, R charge, R discharge, and SOC. Okay, so everything is over here. Fine. Then what I'm supposed to do? I'm going to section this because I don't want these functions to get carried out fully. Okay, fine. So I'm going to put input data. So I'm going to give current as an input. I'm going to give Cn, which is a coefficient of that particular system, as a constant. Likewise, I'm a simulation time as a constant. Everything I'll tell you shortly. Okay, guys, please listen. So far you understood how to read the Excel sheet, how to segregate the thing. This is so much important. As well, in the so what I'm going to do is, I'm going for BAT model. Okay, so here I'm going to read some of the data. Okay, so what data I'm going to read? So I'm going to tell you that Sritul Das, a normal script and live script. So I tell you that there is small difference, not big. I'll tell you that. So from here, the output which I'm going to get is SOC, because that this particular equation will represent SOC. So I'm going to put SOC. So now what I'm going to do is, already I have imported some data of my Excel sheet: OCV, R charge, R discharge, SOC. So now I'm going to implement 1D lookup table. These things are new, guys, so please take a note. So what I'm going to do is, I'm going for Simulink library browser. I'm going to bring in tables, lookup tables. Go for lookup table. In this we have so many lookup tables. Okay, so these tables are like measuring some constants. Okay, so I am just bringing in a 1D lookup table. So what I am going to do from this, I am going to calculate two things from this. So I'll tell you all those. I am just copying this. Since I am going to bring in two, I am just creating two lookup table. So I am bringing the state of charge here. Okay, the input to this lookup table is SOC. So using SOC, I am going to measure the OCV. Okay, so when you see here, we have a state of charge over here. In proportionally, we have open circuit voltage. So for each state of charge, there is particular open circuit voltage. Okay, these things work proportionally. If you know OCV, you can predict SOC. If you know SOC, you can predict OCV. Okay, any one is sufficient. So just double click in this lookup table. I'm going to change this data. I'm going to read OCV from SOC. So how you should put input here? Breakpoint means the value which you already know. Versity means the value which you want. Okay, in the table data, put the value you don't know. In the breakpoint, put the value which you already know. Okay, so after putting this, as you see, the graphs get automatically plotted. Okay, so from this you can see whether you have inputted good data or not. Okay, from this you can verify your input data is correct or wrong. Okay, so now guys, the output from here is OCV. Guys, I hope you are listening. Okay, so the output is OCV. From why we are doing all this? In order to model this particular equation. Okay, first we created the model of this. From this represents SOC. I'll repeat that. Okay, guys, please listen carefully. First we created this. This will become 0. Okay, initial state of charge will be 0, so leave this. Just by doing this equation, I am getting SOC. From that, what I am supposed to do is, I am supposed to put SOC here. I am supposed to find OCV and multiply both. Two things are in multiplication over here. Next, I am supposed to multiply my current with my R discharge. Okay, R discharge. So from this, as you know, this is why I brought lookup table, because I know SOC and I have some data. From that data, I can read OCV. Now I have SOC, I have OCV. So you can easily multiply it. After that, I have a current here. Now I am going to use separate lookup table to measure the R discharge value. Okay, so that you can completely build this particular equation. Okay, fine. Let us move here. Yeah, so that's why I brought separate lookup table. So double click this lookup table. In the bottom, put SOC. On the top, put R discharge. See, the graph got automatically plotted. Different graphs, okay, based on the data input. Fine. Next, what I am supposed to do is, if you go here, guys, please listen, take a note, step by step put a block, so that first you can understand, then you can create a model. We will help you to how to install MATLAB, everything we will help you. Okay, so I brought two lookup table, one for this, one for this. So next, what I am supposed to do is, Mukundan, that's what I am telling. Once again, I'll tell you. Okay, so finally what I am supposed to do is, I am supposed to minus two things, arithmetic operation. Okay, so the function of lookup table is to calculate one value from another thing. So you know, I can plot these two things as a graph, x and y. So if you know SOC, which is a function of OCV, for the state of charge is 0.04, the OCV is 3.5. For 0.1, 3.81. Okay, but while creating a math model, you cannot manually give an input. Then it's a waste of time. Everything is waste, garbage. Okay, these things should be automated. In order to automate these things, even while you create a model for heat and mass transfer problem, everything, you cannot go and find humidity, moisture and all. Okay, everything you can put it in as a graph. So if you use lookup table, if you have one data, it will automatically predict, find the other data. So that's the function of lookup table. Next, what I am supposed to do is, I am supposed to bring in current. Okay, current is nothing but a constant. Guys, please listen, current is nothing but a constant. So simple, there is a constant over here, put it over here. Okay, now the input comes in play. Again, I cannot put current as a constant, so I am going to put current as my variable I. Later I will give so many things. I varies from this to this, I can give. Okay, next, what I am supposed to do is, I am supposed to multiply my I value, constant value, with my my current value with my R discharge value. Okay, that's what I am going to do now. It is product. Okay, it is multiplication. So from here, what you will have is R discharge. From here, what you'll have is R discharge. So what I'm going to do is, the input is this. So from SOC, you're going to calculate R discharge value. Now, I'm going to bring in product. Go here. Here it is, product. So bring in the product, put the product over here. Okay. So now, one data for product is your constant value. Why constant value? Because when you see, one data is your current, another data is your R discharge. Okay. So go for here, go here, connect this data to here. Okay. Now, guys, please listen carefully. I have brought in current, I have brought in R discharge over here. So if you see, yeah, I selected product because I'm going to multiply. Why we did not select? You will only select gain when you have multiplier. Okay. So in this case, see, in here I selected 1 by Cn because it's going to get multiplied. I know this as a constant, but current is not a constant, R discharge is not a constant. So in that place, you cannot use a constant gain. In order to avoid that, I'm going to use a product. Okay, so that's the reason I selected product. So next, what I'm going to do is, so go for that math equation. I'm going to use minus over here. First term minus second term. So go for this. Then bring in the arithmetic operator. Arithmetic operator minus. Here we have. Okay. So put it over here. You can just pull one corner, it will become bigger. Okay. Since we have two things. One is minus, this sign is plus. So that's why I have did that. So double click it, delete one of the plus, put one minus. Okay. So now this data is for subtraction, this data is for addition. That's all, guys. The work is done. Okay. I hope you understood each and every block, everything. It's because there is no point in me just telling something and going. Only if I transfer something, some knowledge to you, then that's, benefit for us. Okay. So once again, I'm telling, current is a constant because in your home you have 2 amps, 3 amps, whatever it is. Okay. So likewise, the current is a constant. As per the equation, what I'm going to do is I'm going to integrate my current. I'm going to multiply that with I'm going to have a gain of that. After that, I'll have a SOC. By using SOC, I'm going to create OCV. From that, I'm going to find R discharge. And as per the equation, I'm going to bring in product and I'm going to create a math operator. Okay. So this is what the equation tells me to do. Next, can you compare the flow of equation with the diagram? Yes, definitely. I'll tell you. So next is I want to take the output. So as usual, as I told, in order to take the output, what I am supposed to do is go for things. I have a scope over here. So put a scope here. Okay, fine. So now I'm going to put scope in some other places. So what are the places? I want to know my SOC. Then I'm going to use a mux. As I already know, mux is used to compare two results. Here I want to compare the input current and output voltage. Okay, that's very mandatory. So go for mux. I am putting a mux here. I am putting a mux here. input current okay, so input current. Next is output voltage. I want to compare the both. Next, copy the scope, put it here. We started from basic. See, now the system is so much complex, I hope. Okay, guys, now tell me what are the unknown variables? Put it in the chat box. So what are the unknown variables? ICN. So Union. So actually in I'm in one place I'm going to integrate my current, I'm going to multiply it with the gain something. In another place I'm going to use my current as a product. Don't confuse it, okay? Very simple. If you want to have a multiplier, if you want to scale the thing, you are going to use gain. It is just like amplification. In all the other places, you are going to use some other based on the requirement. In this particular case, my current is not a gain. It is a basic input. If you take 1 by Cn, it is a constant, it is a gain, it is a multiplier. I used gain. But current, it varies. In our case, I'm going to use 2.3 amps. In your case, it may vary for based on the battery capacity available, it will change. But 1 by Cn will not change. Okay, so that's what I mentioned. In this particular case, it's 2.3. If even if you want to charge your battery at a faster rate, you can go for 4 amps. It will change depend on your facility. Okay. So SOC OCV multiplied, then we have to minus it with the product nozzle. That's what I'm doing. See, I brought, because this term OCV, SOV, this is positive. The product is negative. This is the arithmetic operator. Okay. I hope your doubt got, you're a bit confused, but again, go through this again and again. For a beginner, it will be difficult. Okay. Fine, guys. So I hope you understood. Next, what I am going to do is I am going to define, everybody gave me all the unknown variables. So what I am going to do is I am going to put all the unknown variables in my M script. Guys, very, very important, listen now. You cannot charge your battery at 10 seconds. Okay, at least it will take 1 hour to get fully charged. Okay, so what I'm going to do is I'm going to put sim time. Okay, everything you can customize. So I'm going to put sim time, just save it. But when you put a variable here, you are supposed to define the value for that variable. Please listen, this point is very, very important. I'm going for M script, I'm going to put input data. So input data is I equal to 2.3. So if you put capital I, if you define small I here, it will show you the undefined variable. So please be sure you are putting all capital and small correctly, because this is case sensitive. Okay, next one is I'm going to give Cn, coefficient value, which is 2.3 multiplied by 3600 for 1 hour. Put it in a bracket to avoid the error. Okay, next one is simulation time, 3600. I'm going to simulate my system for 1 hour. Okay, I defined all the things. So go down, I'm going to get an output. Okay, plot. Please mute yourself. First, I'm going to simulate it. Guys, it is a very deadly combination to use scripting with Simulink model. Okay, now I prepared my Simulink model. For these datas, I'm going to simulate my Simulink model. How to do that? What is the command? Sim. I'm supposed to put the name. Okay, so what is the name of our Simulink model? bat_mod. This is why I told your name should be simpler, easily memorizable. Okay, remember, you should remember that. So this is the command to simulate your open, that Simulink model. Next, I'm going to plot the output result. So plot, what are the things which you want to plot? Okay, first thing is I'm going to plot SOC as the function of OCV. Okay, first graph should plot SOC with OCV. Next, separate that by figure because I want everything to be separate. So first thing, separated by figure. Plot SOC R discharge. This is what I calculated. R discharge. Okay, I have two plottings. Fine. So everything is good. Now let me run this. Let me check for any errors. Fine. Our system is so good. No error appeared. Okay. So this is just a warning. Guys, see here. I got two graphical representation. So please mute yourself. So one, this represents, let me check, figure 1, SOC with OCV. So this represents state of charge. It is from 0 to 100%. This is open circuit voltage. Okay. At the 100% state of charge, it means your battery is supposed to have around 4.3 volt. Okay. Sorry, it should be a straight line. Okay. At the full charge, your battery is supposed to have 4.3 volt. And this is the pattern. Your battery will get discharged. At 0% SOC, your battery will have 0%, zero voltage. Okay. So now I hope you understood. Next, when you see here, this is, plottings between SOC, state of charge, and R discharge value. So this is state of charge, varies from 0 to 100%. This is the R discharge value. Okay, resistance while discharge. Okay, guys. So, we have successfully created a battery model. So, if you go for mat model, now I can even see all those things over here. Just double click scope. As you see here, fit it. I have a constant current. Your current is here, 2.3. You have a constant current. With a constant current, what happens is your voltage is going to get increased for the time period which varies from 0 to 3600. It is 1 hour. Your current is going to be constant. Your voltage is getting increased as your charge is, state of charge. Your battery is getting charged. Okay. Exactly. Our Simulink model predicts its behavior. Okay. So when you double click the scope, you will have this. This is what I'm telling. State of charge with respect to voltage. If you see here, gain. So this is nothing but state of charge. So from 0, it is going to 100%. Straight line. Okay. So guys, with this, we have successfully created a Simulink model which behaves exactly as our real-time battery. Okay. So this is how to create this. Okay. Guys, I'm very sure you understood this. Once again, I'm giving a brief intro. Please listen carefully. First, I have an equation something like this. I will compare this. This is where our Indian engineers, researchers fail to create a successful math model. This is where other country peoples plays a lead role. Just by doing some mathematical model, they will be able to successfully publish their paper in a very high reputed journals. Okay. So this is our math model. Sorry. I'm not able to balance it because my screen is so big. My inputs are big. Let me try to do something. Fine. So guys, see here. Okay. So when you see here, I have this particular equation to, sorry, not that equation, only below equation. So I have this particular equation first, which represents SOC. This SOC at initial is 0. Okay, so leave this. So first what I did is I have a current as an input. So current will come from here as an input. I will integrate that. After integrating, integrate of I is this particular term which corresponds to SOC. Okay. So next what I am supposed to do is I am supposed to calculate OCV as well R discharge, which is a direct which has direct relationship with SOC. So what I did is I am using two lookup tables which has an input from SOC. From that I am going to calculate OCV, I am going to calculate R discharge. So in order to multiply my OCV with R discharge, OCV is here, OCV is here, SOC is here. Since it is in direct relation, it will get multiplied, and I am going, since this is positive, I am giving in a positive terminal. Next one is I, current from here is multiplied with R discharge, which represents my second term. Both term is, first term is positive, second term is negative, so positive, negative. Very simple. I connected that to scope to get output. To compare, I use mux. To get output, I use scope. Okay, guys. So please take few minutes to go through this. Very simple. Yeah, R discharge is obtained from table. That's why I used the lookup table. Okay, fine. So I hope you understood. So from here we can take a small break, 10 minutes break. So guys, I'll put this in my screen, okay? So you can go through this. Yeah, very good. Someone asked me some question. Sritul Das, what does OCV and SOC mean in equation? I expected that question from nobody asked me. You know, if something is like this, you know, one block is here and it's coming here and another block is there. If the blocks are in series, automatically the product will get applied. Okay, so that's what SOC here, OCV here, automatically the both thing will get multiplied. That's why I haven't used product and all here. CN actually, in order to exactly model, for example, if you take a mass spring damper, okay, you have something called damping coefficient. You have a lot of coefficients are there. If you take heat transfer problem, we have heat transfer coefficient. That depends, you know, CN is a characteristic of this particular model. Okay, it is a coefficient. So whatever you take, definitely you will have so many empirical values in order to exactly create a model of that. Okay, that is what CN means. It is a coefficient to exactly represent a math model. And again, that's a constant. That because that's a characteristic input. So any doubt, guys? T means the time, Sritul Das. R discharge with respect to SOC with respect to time. Most preferably we use small t, but they have mentioned big T. Time. Because my system is getting ran from 0 to 3600 seconds. So for each second, my discharge value will get changed. No, that's what. Fine. Let us take a break. Time is exactly 6:15. Take a break till 6:30. If I show the script, yes. So go through the script. We will send you, no issue. But go through this model, okay? Because guys, I'll tell you what we are going to see after the break. After the break, we are going to create PID controller manually. We are going to build mass spring damper. I'm going to combine both. Okay, so you are going to see what we can do by simply sitting before the screen. Okay, thank you guys. Please take a break. Yes. So let us start now. I hope all the participants are here. Fine. Yeah. So let us start again. Sir, can you brief scope again? Scope is nothing but creating a graphical representation. It's nothing but output. Okay. So whether, sir, whether RT SOC is in first equation? No, no, both are different. From the SOC, from the second equation, you will find your first equation. Okay. So second equation is a sub equation. Fine. So let us start. So in the screen, you can see something like introduction to control system. So control system is not only for specific departments. If you are a mechanical engineering, then you should, have an in-depth knowledge on control system. And if you are from a EC, triple E, whatever it is, then this is your core. Okay. So whenever we speak about control system, then definitely there comes a term PID controller, proportional integral derivative controller. Okay. So I'm going to give a small example, then I'm going to create a math model. Okay. So I had a lot of models to create, but if if I go on faster and if you don't understand anything, then there is nothing in that. So that's why I'm going slow so that you can understand. If you understood, if you understand one problem thoroughly, with that concept you can build 100 systems of your own. Okay. So that's why I'm telling everything in detail and slow. Okay. So please try to follow me. If you have any queries, please put it in the chat box. I'll try to clear it then and there. Fine. So there is control systems is of recorded session. Everybody is asking recorded session. Definitely I'll check that. No, you'll get that. Okay, no issues. You know Seeing the recorded session is something like seeing a YouTube video. Okay, so try to understand now itself. Any queries, ask now itself. For reference, you can have a recorded session. There is nothing in seeing a YouTube video. Okay, fine. So we have two control systems, manual as well automatic. Manual is nothing but, just assume you are putting motor. Okay, in your home you are just switching on the motor and you are looking at the tank. Okay, so once the water reaches the top, you'll switch off the motor. This is one case. Okay, another case, just assume you have a valve control. So that the tank is getting filled, there is a valve to control it. If you see the water trying to reach the top level, speedily you will try to close the valve, and again after using that water, the water level goes down, you will open the valve, again if it reaches the top, you will close the valve. Okay, in this there is so many things to notice. One is observing. Okay, by your eyes you are observing the level of the water, by your hands you are just performing some operation, closing, opening something. But in between those two, sensing, processing, we have something in between, our brain, which decides what is the level of the water tank currently. And you know uh, screen is not visible. Guys, is my screen visible to all? Fine, thank you. Yeah, it's visible. So please check yourself. So one of the important thing to notice is, your mind will make a calculation, because if there is a valve, you cannot wait till the last point. So water reaches the top point, and if you try to close your valve at that point of time, what happens is your water will overflow. So your mind will make a calculation. Currently, the water is in this level. So if you start to close your valve right now, at the time when it reaches the top, you will be able to completely shut off your valve. So likewise, so many calculations will go in your mind. Okay. So this function is manually done. So if you do this, if you try to do this in Simulink model, then you are going to use PID controller. Okay, proportional control, proportional integral derivative. It's nothing but your eyes is going to sense. It is going to sum up the past error, present error, future prediction. Based on that, your brain is going to give a signal. Your hand is going to make a function. It is going to control the process. Again, based on the output, the thing is going to get in a cyclic manner. It will go on. So that's what given in this particular slide. When you see, you have a reference input. This is nothing but level of the tank, and just forget this for now for time's sake. After that, your brain is a controller. Guys, please. Fine. So I muted. Your brain is a controller based on the current. Just a minute. Yes. So sorry. We can continue. So based on the brain signal, brain will give a control signal to your actuator. From that, you will get a variation that will cause disturbance, that will simulate the process. From that, you will get the output. That output will be sensed by our eyes. Again, it will be fed here. Both the signal will be compared. The difference will be found as error. It will be again, it will go in a cyclic till you reach your need. Okay, so this is manual. So next is, so if you see, this is automatic control. Okay, so automatic controller, in the place of human brain, we are supposed to have a chip. Okay, so this will decide. So in the place of human hand, we are going to have a servo motor. Okay, so this is replaced by chip, brain is replaced by chip, hand is replaced by servo motor. The sensor will be replaced by some sensor. Okay, so there will be output, it will be sensed, fed, level of the tank will be fed. Based on that, controller will take a decision. From that, it will give a signal, actuator will perform. After that, it will create a output variation, a process will get done. Okay, so this is automatic control. So this is what we are going to create a model as of now. Application, you cannot tell this is the application because everything is automated. So from this you can see, from a processing tank to a EV, everything depends on control system. Okay guys, fine. So this is just an example. So next, I'm going to go into our topic, how to create it. So please listen carefully. So this is our PID controller. Okay, so if you see here, we have three definitions for the three term: proportional, integral, and derivative. P, first term P, represents, guys, I'm going to give you an example. For example, just like, your water is getting flowed in the water tank, and what you are doing is you are just, the water has, 1 minute. Yeah. Annotation is not working. Fine. So we have a proportional term, we have integral term, we have derivative term. Okay. So what is proportional, what is integral, what is derivative? Let us see now. For example, guys, please listen carefully. You have your water tank and you sense it, the water is going to reach the top level at a faster rate. Okay, you missed something. You was just saying somewhere, you missed that the water is going to reach the top level but not yet reached. what you will try to do is, you will speedily you will try to close the valve. Okay, so that is what P, proportional. It is directly, it will be in direct relationship with the present error. Okay, uh, if you want to tell it in Simulink term, it will be gain. You will put effort at a very faster rate only based on the present error. Okay, that is what P means. It is present error. Next one is I, accumulation of error, nothing but integration. So if you only have P, then your system is not a smart system. Okay, if your system is a smart system, it should see the past, it should predict the future, it should work on present. That is what a human brain will does. Because most of the time you will work on your motor on day-to-day basis. So if you start closing your valve, at what time you can reach the tank top level, that, right? Based on that, because that varies in each person's house. Okay, only the person who works on that daily know that, because if I go to a random person house and if I try to control that, definitely I'll make a mistake. Okay, but in my house, what happens? We know the past error, we know what will be the future, I know the current level. So based on that, I'll take a exact decision at exact time, so that my system will be a smart system. And if you want to do that mathematically, if you want to build a smart system, then PID controller comes on first. Okay guys, so I hope you understood the concepts. Now I'll tell you very, very simple. Now I tell you how to create a PID controller manually. There is automated PID controller in Simulink, but if you know how to create it manually, using automatic is very simple, like a piece of cake. Okay, so okay guys, let us go into Simulink. If you have any queries, you can ask now. I am going to build two systems now. Okay, one is mass spring damper. Sorry, I forgot to future. So that's what I told. If you use I, integral term, that is accumulation. It will see into past errors. From that, it will create a value. Okay, that value will be compared to the present error. So based on the past and present, your system should be able to predict your future. That is what derivative term. Okay, as I already told, around 8th grade, I tried to check whether differential calculus works good or not. At that time, I realized it works good, because at that time we don't know what is differential, integral and all, but now it is live for all. Okay, so by using the differential term D, you will be able to predict what will be a future error. So based on this three, past, present, future, you will create a control signal that will smartly control your process. Okay, so let us move now. So already I have created a PID script that's advisable. Next is I'm going to create a Simulink model. Fine. So guys, we are going to exactly model this. Okay. So we are going to exactly model this. Fine. So as you see, we have KP, KI, KD. So I'll tell you how to tune all these things. But as of now, put in your mind, these things are constant with respect to each and every system. Okay, these are the characteristics constant of a particular system. Like that, have it in your mind. I'll tell you how to tune this once we saw how to simulate a mass spring damper. Okay, fine. So if you see present error, it is nothing but gain of your error. So go through this. Okay, first is nothing but a gain, second is nothing but integration, then differentiation. Okay, so since we have Kp which is in multiplication, Ki which is in multiplication, Kd which is in multiplication, so whenever multiplier constant comes in play, we are going to use gain, and I'm going to use my error term here directly. Okay, there is nothing we should do here. But here I am supposed to integrate my error. Then I am going to, yeah, one minute, 1 minute. Yes. So first, in this case, I'm simply going to use gain because error into gain. Okay. Next one is gain of ki. It's a constant. I'm going to integrate my error for the time of 0 to t. Okay. Next is I'm going to multiply my gain with my derivative. Finally, I'm going to add everything. Okay. Input is error, output is process. Okay. So let us try. Very, very simple. Guys, please, listen, because most of the time students are interested in getting a certificate, but the paper is just a proof to tell you you have some knowledge in that particular topic. Without having a knowledge, the paper worth nothing. Okay, so please, listen step by step. Fine, I'm going to save us. I'm going to name this as PID. Go for Simulink browser. I am going to bring in gain. Control drag, you will get the copy. Okay. So first KP, proportional term. Next KI, integral term. Next KD, derivative term. Fine. I am going to bring in input. Input, I am going to bring in output. Okay, output. So input is there, output is there. If you click it, you will be able to see the input. Fine. So connect this, connect this, connect this. Okay. Next, what I'm going to do is all the things are added. Okay. All the things are added. So before adding, when you see this particular thing, everything is get summated. KP, multiplication of error, integration, differentiation. So this is what we are going to see now. So guys, please listen carefully because I'm not going to do a new PID controller for my mass spring damper. I'm going to copy this. I'm going to use it there. Okay, fine. So now I'm supposed to bring in integrator. So bring in one integrator, bring in one derivative. If you frequently go through these inputs, you'll be able to find all those. I'm supposed to find my derivative because I haven't used that frequently. Derivative. Yeah, it will search the entire library. Derivative, yeah, it is in the first place, sorry. Fine, so put it here. So derivative term for kd, and for ki I am going to use this. Just try to connect it. Inian, you are supposed to answer me that. Why we are using 3 gains? Okay. So next what I am supposed to do is, I am supposed to add all these. So go for this add. Okay. So pick and place sum. So as you see in this sum we have only 2 inputs, but currently I am supposed to feed 3 inputs. So in order to customize, just double click, put 1 plus over here. Put 1 plus over here. So you'll get 3 inputs. As you see, we don't have inputs in a proper gap. In order to have that, please remove this line so that everything will be 90-degree gap. Fine. So I'll connect this. I'll connect this. I'll connect this. Take output. This is what PID means. Okay, creating a mathematical model of PID in Simulink. Okay, very simple. So save this. So this is nothing but error term. Error. So you are going to see the past error. You are going to predict the future error. You are going to see the present error. Okay. So based on that, you are going to differentiate it, integrate it. You are going to build your PID controller. Okay. Guys, the procedure is same. Whatever smart system you are going to build, this is the procedure to find your, to build your PID controller. Okay. But with this, you cannot validate whether you have made your correct PID. Like that, you cannot verify, because this is just a controller. We don't have a control system, control input. We don't have a control output. Nothing we have. We simply have some blocks. But how to validate this? This is what we are going to see right now. Fine. Guys, please, if you have any queries, please ask me now, so that I'll move on to mass spring damper. So this is how to build a PID controller. But in order to validate this PID controller, we should need, we need some system. That system I'm going to assume as a mass spring damper. Okay. With that, I'll create a mass spring damper. I'll put this in there. I'll show how things work, how system works. Everything can be visualized, witnessed. Okay. Guys, any doubts? Most of the time mechanical guys feel like these things are irrelevant. But if you think like that, then definitely you are not going to be a smart mechanical engineer. Okay. Even easy triple peoples can miss it, but mechanical people's not supposed to miss this. Why we have not considered ET? Because the ET is nothing but error with respect to time. That is the input. So I am just multiplying my KP with my input. So I have considered that. Fine. So some of your doubts can only be answered with my system. Okay. Yeah. So let me proceed now. This is the PID controller, guys. I forgot to tell you one thing. So what we can do is just select all, right click, create a subsystem from selection. What happens is you can completely put all your things. This is how your thing works. You can user definedly create your system. So with that, you have made so many programs. I have just made that into a single block, because this is how your PID controller works. If you want to get back, just right click, go here, create subsystem. The thing got expanded. I'm supposed to pull in here. So I'm bringing in here. Likewise, I'm supposed to bring this over here. Okay, so guys, once again I'll do that. Oh my god, yes. Okay, because these all blocks are not a separate block. It is a single PID controller. So to make that, select, right click, create subsystem from selection, so that everything will get converted to a single block. This is how the automated block in Simulink works. Okay, okay, let me proceed now. Okay, so I'll create my mass spring damper over here. Okay, so that, okay, I'll create it in a separate thing. So go for new model. I'll save that as mass spring. Mass spring. Okay, fine. So guys, this thing is going to be a bit confusing, but no, listen. First we modeled PID controller, we have that. In future I'll bring it here. Okay, so next I'm going to tell you something about mass spring damper. Okay, fine. So I'll put it in the screen. Okay, so this is both. So this is both, we have a mass, this is just a representation of a practical suspension system. Okay, we have a mass, we have a spring which is loaded. If you don't have this particular damper, what happens is the thing will be like no damper. Theoretically, your car will like a horse. It will be jumping, going up, going down, going up, going down. Okay, that is, we can't afford that. It is funny. So in order to arrest that free vibration, I am going to use a damper. So when you use spring with a damper, as you see, automatically the thing will get arrested. Okay, so this is what we need. So you are going in a car, accidentally you are driving up a speed breaker. There is a force generated. That force will put a mechanical effect on spring. The spring will start to vibrate. If it vibrates without control, it is going to be like a horse. If you want to arrest that, I'm going to use a damper so that my thing will get decayed. My vibration, my up and down effect will get decayed, and at one point of time it is going to reach my steady state. Okay, so this is called mass and spring damper. Okay, so likewise there are a lot of electrical system based on this. Okay, mechanically we are speaking about damping. When you move on to electrical term, there are a lot of things controlling the signal. A lot of stuffs are there. So if you represent that thing mathematically, you will have this particular set of equations. Don't get scared of this. Very, very simple. So by using Newton's second law, force equal to mass into acceleration. So mx double dot, mass into acceleration. Acceleration is nothing but double derivative of x. Okay, so that is what mentioned as mx double dot. Okay, guys, please note down. Already force equal to mass into acceleration. Mass we know, acceleration we know. So this is on the left hand side. On the right hand side, this is the net force. Okay, F is nothing but the force which is a pulling force. In case of car, it is a force which is generated because of the moving car getting ran over the speed breaker. Sudden jerk. If you are driving in a bike, you can observe that force practically. Okay. Next one is B into x dot. Okay. So when you see here, we have a stiffness here. Stiffness is the property of the spring. If this is pulling this side, the stiffness will pull the system this side. Okay. Likewise, we have B as a damping coefficient. Again, I will write it. Guys, please listen very carefully. K is the stiffness, which is of spring. B is a damping coefficient. Okay. So this two force is going to pull your system this side. This force is going to pull your this system this side. So that is what? This is the net force acting on your system. F on positive direction, these two terms on a negative direction. Okay. So if you expand your thing, then your system is going to look like this. Okay. Now what I am going to do? So now what I am going to do? Guys, please listen carefully, very, very carefully. I am going to make a small thing. So that's not given in the slide. Guys, do one thing, okay? Bring this particular m to this side. So what happens is the whole term will come within one coefficient. So the whole term will come in multiplication by 1 by m. So this 1 m will go. So acceleration, which is generated by the force, is equal to this. Okay, that is what I am going to do right now. Please take a note, write this. Okay, write like put x double dot one side, put your mass on the other side, so that you will have one math equation. So what we are going to do is, we are going to create a Simulink model which is going to represent this. Okay, guys, so far we have created a loop, but this is not a loop. The force is an input, the acceleration is output. We are going to compare everything. Okay, so I'll do these things speedily. Okay, try to follow me. Go for mass spring. So any idea what I'm supposed to bring in first? I want inputs from you. Go through this. What is the first thing which I'm supposed to put it in my Simulink model? Force. Good. Practically force is the input, but in order to create a Simulink model, we do what we do? We use derivative, integration, something like that. I'm asking in that. Somebody gave me answer. Derivative. But how derivative? Okay, so I'll tell you. First, I'm supposed to use integral. Why integral? I'll tell you. Okay, so what I'll do is, I'll try to snip this. So guys, at the end of the session, I want everybody to be able to create a Simulink model. Okay, so paying some 499 or 399 rupees is not a matter of fact, because we have given free access to students who have 80 CGPA and all, CGPA about 8. So I want you to get something out of the session. Okay, so that's why I'm going so slow. So please take a note, write it down. So we have so many things open. So I'll open this. Okay, we will have this on site. So go for mass spring, go for Simulink browser. I'll have this here, I'll have this here. Fine. So we can see that parallelly. Okay, fine. So guys, as you see, at the output we have differential term. Okay, So we have m. I brought that m to the opposite side on the left hand side. So I am going to have differential term. It is like x double dot. So on the left side, I am going to have x double dot. So from there, I am going to start. Okay. So if you have your, guys, please listen. X is an input. Okay, I'll tell you. So first, let me assume my output as an input. My output is x double dash. That is nothing but acceleration. If you integrate your acceleration, you will get your velocity. If you integrate your velocity, you will get your distance. Okay. So here distance is nothing but the distance which is which the spring will get compressed. Okay. Practically, when you see, I have my spring like this. There is a sudden force. Because of that, I'll get my spring will get converged. So this is the final length. This is the initial length. So this is change in length. Okay. So this is what? So you have your acceleration. If you integrate your acceleration, you'll get your velocity. If you integrate your velocity, you'll get your distance. Here, distance is nothing but distance traveled by your spring. Okay. So first you have your acceleration. Okay. So I'm going to bring an integrator. Why? Because we are going to, I have x dot dot. I'll put x dot dot. That is nothing but your acceleration. Okay. You are going to integrate your acceleration. From that you are going to get x dot. That is nothing but velocity. Very, very simple. Okay. Upside down. Next, I'm going to create a pattern. Copy this. If you integrate your x dot, you are going to get x. Guys, understood? What I am bringing as an input? I am bringing the output as an input. Okay, acceleration. Fine, good. This is what I need. X, the distance traveled by my spring. Okay. Next, what I am supposed to do. So go through this equation. We have three things. One, my F, force. Next, B, my damping coefficient multiplied by my velocity. Next, my stiffness multiplied by my x, distance. So as you know, B is a damping coefficient constant, K is a stiffness which is a constant. So I am going to use what? Gain. Guys, you can just try, okay? Because lot of people in MTech level or PhD level are creating so many prototypes, testing so many things. While trying to publish those, most of the time you'll get so many queries. But if you add this math portion with that, I'm telling you, your paper will get accepted just like that. Okay? So that's the importance of this. So what I'm going to do is, I'm going to bring in gain. So I need two gain. Guys, I'm going to rotate it. Go here, flip block. Okay, because I'm going to have, I should have in that direction. So my x is going to get gained by k. I'm going to use minus k. Okay, if you use minus here, at last there is no need to use minus in arithmetic operator. So minus stiffness. Okay, this is stiffness, x multiplied by stiffness. So you got your last term. Exactly, you got your last term. Next, I am going to copy this. I am going to put it here. This is damping. Okay, so damping is nothing but minus of B. Okay, next, I have my force as an input. Here I am going to use something called step. Why step? I'll tell you. Yeah, step is here. So step. So I'm going to use a step input, that is F. I'm going to put F here, okay, all in small letter. So now when you see, we have successfully created F minus B x dot minus kx. I have those terms over here. Step, all these things are here. 3 terms are here. So why I used step? Because while you are running over the speed breaker, the force will be like this, sudden jerk. Okay, so that is why step. Okay, sudden jerk. In a particular time, you will have a sudden jerk. Okay, so that's why I use step. So I'm going to use a arithmetic operator here. So go here, guys. The things which we are seeing here is vast. Please listen. Don't get bored, something like that, because these things are important. So I am bringing here, double click. I am supposed to bring 2 inputs here, 3 inputs here. Put F, 1 here, 1 here, 1 here, and the output here. That's all. Our thing is done. But no input is here. Everything is a variable. F minus B minus K. No inputs we have given, but we have created a dead model. We have to create an input and make it a live model. So in order to get an output, I am supposed to use scope. In order to measure the X, in order to measure the input force, guys, I am supposed to compare my input force with my displacement. Okay, in order to do that, what am I supposed to use? I want to compare 2 signals. So what is the component? Good. Fine, thank you. So I'm supposed to use mux. So go here, because only when you compare the both you can know. So I'm going to take the output from here. I'm going to take the output from here. Okay, copy one scope here, put it here. Okay guys, so save it. Fine, it is done. As usual, here put simulation time. What is here? Simulation time. Save it. Now what I am supposed to do? Here everything is F, something like that. So go for your MATLAB script. Go for your MATLAB script. Define your values for all. So F equal to, we forgot a very big term. What is that? We forgot 1 by m term, which is a magnifier. So it is like one side, so it has to go on the other side. So I'm supposed to use my gain over here. Go here, gain in between. Okay, put it here, double click it. It is like 1 divided by m, which is the mass of the system. That's all. Check it. Fine. 1 by m. Okay, so save it. So go for MATLAB script. Force, I'm going to give 1. Okay. Mass, I'm going to give 1 kg. Unity. K, I'm going to give 20 Newton per meter. B, I'm going to give 10. These are the inputs you will get. Okay, damping coefficient, stiffness, mass, force, everything you will get as an input. Okay. Next, sim time. Simulation time, I'm going to put as a 7. So it can vary. 1, 20, 10. Simulation time equal to 7. Okay, it can vary. It depends on your input. I gave my inputs. So what I am supposed to do to simulate my Simulink model over here, what is the command? I already have my Simulink model. I want to, I have my Simulink model name as mass spring. Very good. So go here. What about the units of given parameters? So everything has its own unit. Okay, force Newton, mass kg, stiffness Newton per meter, damping coefficient Newton second per meter. Okay, so in the comment you can put your units. So that I mentioned on Monday itself. Comment you can put your units. So something like that. Newton. When you come down, you can put something like kg. For this stiffness, I'm going to put like Newton meter. N is in capital. So all n should be in capital. Okay. So that those things you can put it. Just a unit. Okay. So exactly. Very good. So sim open bracket mass spring close. Fine. If you are missing any input, it is going to tell like unknown variable. Guys, see here, see all our previous data are here. Battery model, everything is here. Okay, so in order to get rid of this, what I'm supposed to use, because those things will create a mess. Okay, so everything seems good, so run it. We have a copy, it seems. I think we are making a big mistake. No. So names is very important. If both name are same, then things like this will happen. Okay. So save. So run. Superb. These are simple warnings you will get while trying to run your Simulink model in script. No errors. Fine. So now go for mass spring. Now I'm going to show you some of the graphs. Okay. I'm going to show you what is the acceleration. I'm going to show you what is the velocity. Save this. Again, I'm going to run this. Each time, run it. Fine. So go for mass spring, open your acceleration. So you will have something like this, a sudden jerk, upshooting. This is because at time 1 second, we have simulated the system from 0 to 7 seconds. You can vary. At 1, I have a upshooting. My acceleration goes down because of the force acting. Again, because of my damping effect, it is coming down, it's going, again it's getting stabilized. Okay, this is my acceleration profile. You can see your velocity profile. This is your velocity. Okay, from 0 to 1 it is nothing. At 1 we ignite our force, it gets shooted out, goes up, because of our damping it comes down. Okay, it gets stabilized. Okay, the main thing which you want to see is the comparison. When you see here, guys, this is where we want to put PID controller. Okay, when you see here, there is a step force, sudden up force. Okay, to this my system respond. We saw how the acceleration profile was there, how my velocity profile was there. But after that particular jerk, my system haven't come to its own thing. It means my spring haven't came to its original position. It is repositioned. See, completely it is repositioned. This is because of a error. Okay. So this is what we are going to fix it. Step setting, you can open. Step time, you are going, if you put 0 at the beginning of the system, you are going to have that. Okay, my final value is f. For f, I put 1 in my script. Okay, so at 1, at 1 second, the force of s is, f is going to act upon my system. For that, my whole system is going to respond. Then you see now, it is a very, very complex system. But since you have listened, you know how each and everything is positioned. Okay, guys, I hope you understood. You have your acceleration profile, you have your velocity profile, you have your x, how your x is. After the force, my thing is permanently deformed. Okay, it haven't reached its original state. That is because of a error. Okay, so this is what we are going to fix using our PID controller. Guys, any doubt in this? This is a mathematical model to show your I'll tell you that this is guys, so this model is a mathematical model to represent your mass spring damper system. Okay, so error means as I told, when trying to control your system, you'll do it fast, you'll do it slower, you'll have your present error, you have your past error, accumulation of error, everything will be there. No, because of that, your math model will not behave exactly as your original model. Okay, very good. This is what I expected. You can put those doubts in public. How to eliminate this error? In order to eliminate this error, in order to create an exact model, you are going to bring in a PID controller. Okay, so guys, if you understood how to make a, this is a separate project, but we are just putting in this in a control system part. Okay, so guys, if you understood this, we can move on to next topic. Understood? Any doubts? Others? Fine. So what is the function of step? Jerin, function of, you are missing the point, I hope. Function of step means it is the force input. You are driving a car in a smooth road. Suddenly you will come across a speed breaker. At that point, a sudden force will act on your car tire. The force will get transferred to a suspension. So it is a sudden step, upshooting in force. That is what step is doing here. If the force is acting on your system constantly, then you can use some constants. Okay, fine. I hope mostly everyone understood. So I'm going to bring in a smart system here. I'm going to stabilize the error, everything. Okay, let us see. In order to do that, if you are from a if you are from a circuit branch, then signals comes into play. Okay, so as far as mechanical is concerned, forces here. If you are going to magnify a signal, process a signal, you can put that particular signals here. Okay, electrical impulse, whatever it is, it depends on you. Because you can model a short circuit here. How? Because short circuit is because of sudden upshooting in flow of current. Okay, in that case you can put current as a step, sudden upshooting in current. Likewise, you can put whatever variables you want. Okay guys, fine. So now what I'm going to do, I'm going to club two things. I'm going to club my PID to there. So copy, Control C, go for PID, put it here. Okay, see how complex your system is getting, but you know how the things are divided. Fine, so we are going to I'm going to remove this because guys, it may seem a bit confusing. Okay, so I have sir except x it has to come down, no, union. It it upshoots upper. After the force gone, it has to come back to its original position, or else what will happen to your car? If you come across 10 speed breaker, what happens? Your suspension system will go. Okay, that is not the exact function of your suspension. It should go in, come out, go in, come out, go in, come out. Likewise, it has to function. Fine, guys, see, in the place of input I am putting my step. Okay, then so the place of out, I'll delete this. I just made this for PID because now currently I'm connecting that to a practical system. Okay, so I routed my PID controller into my particular system. Input is to PID, output is to my mass spring damper. Okay, so some things are confusing. I'm just deleting this. I created these things to explain you mass spring damper. Fine. So next, what I'm supposed to do? I am supposed to feed my error here. So how to do that? Go for Simulink browser, bring in this, because this you can see from this, from that particular slide. You see here, your error will be there, your output will be fed to this, that thing will be fed to your PID controller, your process. Okay, so now it is going to be a closed loop system. I copied this, go for PID. Now what I am supposed to do? I am supposed to put this here. Put this here, bring everything to here. Okay, now what I am supposed to put here? My output. Output is nothing but a distance traveled by my suspension system. Okay, that's all, guys. So I have just clubbed it. Okay, how I clubbed it, I'll tell you. Listen carefully. First I had input for my PID, output for my PID. Now, in order to couple it with my practical system, I have step force. Before coupling, I want to know what is the exact signal. In order to know that, I want to know the error. Okay, so in order to predict the error, I took from this, I gave. From this, you will have output that will be fed to my PID block. From this, based on the present, past, future, it will create output signal that will be fed to my mass spring damper. Okay, so from that everything works fine. So in order to simulate this practical system, why are the controllers are in parallel, not in series? Because we are going to add that, you are not going to multiply that. Okay, fine. So go for scripting. Here I am going to add those constants KD, which means, sorry, KP, which is present error term. 200. Guys, you may feel like lost, I know, because things are getting complex. So I'll explain this again, okay? So don't worry, try to follow me. Very, very simple. We are just building this in block. First, we build this. You know, this will be easy when you take your note, and if you have made all these block diagrams, then definitely you will not get lost. But if you just visually seeing, definitely you will feel lost, okay? So you have your PID here. This is the comparison term, okay? Fine. There is some doubt. Why subtract displacement of spring and force? No, actually, oh my god. Fine. So actually, that is what Aditya, I told in the first place. You are just trying to close your valve, okay? That is in, let me consider RPM, okay? You are just trying to close your tank level control by using your hand, but the output is what? It is distance, okay? The tank is getting filled, okay? Both things are different, but when you sense it, only when then you can compare it, okay? Only when you compare it, you will get an error term. From that error, the PID will process and create what signal should it have, okay? So it is just for the purpose of comparison, okay? It's not like same something like that. It is comparison. Fine. So we are comparing it. We are giving it. Okay, fine. Let me run it. So go for scripting. So first I am going to simulate a system which is purely proportional, only based on my current error. So how to do that? Put KI term 0. Okay. And KP 200 derivative term 0. So that now you will understand. Now your system will only consider the gain term. It will not consider the integral term, past error or future prediction. Okay. So any other unknown variables there? Everything we included, I hope. Fine. Sim time. Go here. PID. PID. Okay. Now I am going to carry out for the same time. Everything is same, but only I have included some tuning terms. Okay. I'll tell you how to tune the PID controller, everything. Then you'll understand. Okay. Now I'm going to have a KP constant value of 200, which means it is proportional in nature. My system is only proportional. It only considers my present error. Okay. Let me see what happens. Save it, run it. Okay, again the name clash. PID mass. PID mass. So run it. Superb. Fine. So now I'm going to make a plots over here to show the difference, because a lot of students had so many doubts. No, I'll make a plots so that you'll understand how things work. Guys, I forgot to do one thing. I forgot to uh, export my data to script. You know how to do that? What is the role of OP of PID? What parameter routine? Yeah, I'll tell you. I'll tell you, guys. Uh, Now I'm going to export all of my data to my M script. So how to do that? Go for things. We have out here. I am going to name this as it's already I'll make sure that everything is in small. Out and my input. Okay, so if you compare your input with your output, you will understand that. Fine, so save it. Everything seems to be fine. Again, I am supposed to run it. Guys, so far you understood? Any doubts? What is the role of OP means? Mukundan, I'm not getting your doubt. What is the role of? Oh, fine, fine, fine. You are asking like what is the output of PID in a spring damper? Yeah, that is what I'll tell you now. Okay, listen. So guys, any other doubts? So far understood? First we saw how to create a math model of a battery. It is a very big topic and we saw everything in step by step. Now after that I shown you how to create a PID controller. After that I shown you how to create a mass spring damper. Now I'm going to convert my mass spring damper as a smart system. Okay, that is based on past, present and future errors. Okay guys, fine. I got your doubt, Mugundan. I'll clarify it shortly. Fine. So small spelling mistake. So plots. So go down. What I'm going to do is I'm going to run it again. Fine. So first I'll input figure. Plot. I'm going to plot in input data with respect to time, comma, input data with respect to data. Okay. Again put figure to segregate it. Or else you can do one thing. You can use a command something called hold all, so that you will plot the thing in the same graph. Okay, hold all, plot output, out dot time, out dot data. Okay, so run it. Let me see. Plot PID mass, PID mass in out we have T out, Y out. No, no, that is the, it will get the, Sri Tuldas, these things are predefined, okay? Based on the thing which you give there, it will get simulated. We have some other issue. In time, out time, in data, out data. we'll have two things here. No, is hold all means I want to plot two plottings in the same image. Okay. Undefined variable in or function dot in time. Yeah. What is the problem? Fine. I'll do one thing. We can create a mux here and verify here so that we will be able to find out the error. Just showing me. Fine. So go for that particular system. So I'll just remove all. I'll just run it. Fine. So everything is good. Only because of that particular command we are getting error. Let us see now. Let me have this. So go for here. I'm going to bring in max. We have scope here. So I'm going to compare my input with my output. Okay. So bring in one scope here. Just connect it here. Fine. So guys, everything is fine. That one plotting is a problem. So I'll try to plot that in a Simulink itself. Okay. I'll try to figure out what is the problems. Fine. So everything runs smoothly. Now what we can do is just open the scope. Superb. So as you see, no, I'm not getting what I want. So gain 3, I have defined that as particular mass. Mass is 1. Sometimes we may face some errors like this. This will be like small errors because of dot capital. If it gets unmatched, we will face issues like this, but very difficult to sort out. If it is a technical error, we can sort out. I have an input. I have x. I have a x. It's running smoothly. What I'm getting at output. Oh, maybe my time is not sufficient, I hope. Sim underscore time. I'm going to give 20 seconds or else 60 seconds. What happens is sometime my time will not be sufficient. Time is good. There is no name clashes. Guys, sometimes we have to troubleshoot like this. Okay. So finding the issue is difficult. Issues like small capital and big letters will have a fine. I'll explain everything. That's not an issue. But now, yes, both is working fine independently. Uh, error signal. Okay, let me try to open the thing which I already made. Bat model, mass damper. Mass spring, it is fine. Guys, 2 minutes. Because if you face a issue, definitely we have to troubleshoot that. We have to find the error. So everything was fine separately. This is PID. Yes, thus. Error is also for good. Yeah. Guys, please try to verify the connection. If any issues, we can fix it. It's coming. We are connecting X. So it is coming and joining here. Guys, please try to find the issue because both systems are fine. Let me do this once again. Simulation time. Step force is not getting applied. F is here. One we are giving. Okay. Time of the step time one. Let us try this. I'll simulate this PID. Simulation time KI F I gave. It has initial value should be 0, step time should be 1, final value should be F. We have defined the F. Okay, let me try to run this. Same error. I'll try to save this as a different name. Different name. I'll put it in new ma, new mass, new name. Fine. So go here, new name. Okay, so let me try to do one thing because so many files in the same name may clash, create a clash. So I'll try to save the separately. Okay, so go for this, save this particular script, new folder, new script. Okay, Fine, this is saved. Next, go for new mass. Fine. So save this also here. Go for new. I'm just saving in a new name. Okay, because even this may have a issue that will not able to find a file. Some clashes like that. So I'll verify that. New folder file. I have my new mass, new script. Okay. Now go here. New name. It is new mass, no? New mass. So my script is of new script. My mass is of new mass. Fine. Let me try to run this change folder. Superb. Fine. So we had a small name clash. So now let me verify this. Go for Simulink browser. I'm going to mux it. Okay, I'm just going to compare it. Input signal. I'm going to create that with my output signal. Okay. So guys, I hope you are just seeing creating a math model is not only going in a one hand, also it's troubleshooting. Okay. So troubleshooting is very important. I saved this. We had a small naming problem because in that particular folder, I have so many things named similarly. A PID trial likewise. So I hope I have run one script with a separate Simulink model. Okay, the thing got changed, I hope. So that's what I saved at a new script and a new mask. Now I want to see the correct result. Simulation time 60. Fine. So go for new mask, double click it. No, 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 it's not working. Okay, fine. One thing I'll try to do. Yes, yes, maybe the issues I hope only in there. In input signal to this output I am feeding here. It seems this is correct. Bottleneck problem. Mass dump. Simulink PID trial. Just a minute, guys. I'll try to solve this. Fine. A very, very small mistake. In the place of plus and minus, we have included only plus. So what happens is the error will get added. Oh my god. Fine, fine. See guys, how much you know concentration we have to give in. Fine. I'll see this. So plus. So all the other thing is fine. Oh my god. Okay, no issues. So go here. I'm just running this particular script. I hope now it's good. Now what I'll do is go for new mass. I'll try to open this. Ouch. Guys, fine. Only one small thing, okay? Instead of plus, I mentioned minus. The whole system got collapsed, okay? So just assume, just see how much concentration you have to put in. So guys, fine, everything is working good. The small mistake, okay? So when you see from this graph, at time 1 second, the force is getting stepped up and the force is acting on our system, okay? So what happens is, our system is getting displaced, overshooting, going up and coming down, getting settled, okay? So now I'll show you one thing, okay? In order to verify that, I tuned some of the things, what happens if you put only your proportional term, just run it. You witnessed what happened if you include present, past and future error. My system is so smooth. But if you include only your present error, what happens is, see, it will not get settled. So this is the error which we saw at the first place without using PID controller. So this is the overshooting. This is the force. My thing will get overshooted, go down. It will not get stabilized. Okay. There will be a deviation. There will be error. Okay. So in order to fix this error, we have to see on the past error. We have to predict the future error. Okay. So while doing that, what I'll do is I'll include my terms. Okay. So 300. I'm just putting 50. These are some constants. Okay. It depends on your system. I'm just running it. Okay. Now go to, I'll close this. I'll go to new mass. Now open this. What happens is after some time, your system is getting stabilized. Okay. This is what we want, because you are going in a car. It is getting stuck. Force is getting acted in your suspension. Your damper is just damping your unnecessary movements. And after some time, what happen? Your system will come within to its normal position, within 2 seconds. Within 2 seconds, your system is nearly coming to its stable position. Okay. So this is what we want to simulate today. Okay. Very, very small mistake. In the place of plus, we put, the place of minus, we put plus. It added up the error. It completely messed the system. Okay. Fine, guys. I hope you understood. Okay. So this is the graph which shows that. So now we can do one thing. Okay. We can export all these things to my workspace. So put a workspace here. How to do that? This is in. Copy this, put it here. X is your output. This is out. Okay. I am just going to export these things to workspace. With this, we can end. run it. Fine. So I'm going to create a plot. Plot time. Okay. I'm going to plot this with time with respect to data. Figure hold all plot out with respect to time out with respect to data. Fine. So just try to plot it. You will get the same graph here. See. Okay. So this is what I was mentioning. So force will ignite. It will get stabilized at 1. At 1. Your system will respond. X will vary, overshoot, stabilize. So this stabilization is only possible, while considering your present, past and future error, guys. Yes. So successfully we made it. Okay. So any doubt, guys? Definitely while creating a model, you will face lot of issues. Okay. If it is a technical issue, you can easily find out. If it is like capital issue, name issue, something like this, negative, positive, again, this is going to be a headache to find out. Okay. Guys, any doubts you can ask me now. I hope everybody understood. Yes, Inian, how to calculate the range of error values, KP, KI, KD. This is termed as tuning of my PID controller. That I'll tell you. Okay. If you understood so far, that is very, very fine. Okay. Because take your heat and mass transfer book, take whatever book you have, take an equation in that, put an input, solve, you can verify. Okay. Then you will be expert in that. Okay, guys. So just to brief, first we saw how to create a mathematical model of a battery, simulate that, validate that. After that, we saw how to create a PID controller, what is control system. After creating a PID controller, what we saw is how to create what? How to create that PID controller and mass spring damper. After that, we saw how to couple that. In coupling, we made a very small mistake, but that missed our solution. Finally, we sorted out. Okay, guys. So this is what we saw today. We will share you the video lectures. The only thing which we want from you, independently you want to work in this. Okay. So that's all. I hope you understood. I'll give next 5 minutes for doubts. If you have any doubt, you can ask me. Okay. Workspace setup in Simulink again. Physically, what is done by a speed? Actually, Mukundan, in the place of, as I already told, in the place of PID controller, you will have a chip and all. Okay. So everything is smart. So that chip will decide, sensor will feed the current. For example, I'll tell you this exact. Okay. Just assume a spring. What happens is, if the spring is not in a correct position, that data will be shared to a controller. Controller will give a signal to the damper to lose it, so that again it will come back to its normal position. Okay, everything is electronically controlled. Yeah, I'll share the day 2 lecture in here. So guys, any doubts? Why output of PID given to damper? Output of PID given to damper. Where? Output of PID given to damper. I think you are a bit confused, Karthik. Please go through this. I'm not able to get you. Output of PID given to damper. Where we have given that to damper? No, we have given that to this. Okay, this is as per the equation. Okay, guys. So I hope everybody understood. If you have any queries, you are free to ask me. Yes, definitely. Before starting tomorrow's class, I'll shortly explain today's session. Okay? Okay, guys. Thank you.